Great, so welcome to the, I guess, the late afternoon session. The first talk we have is from Li Ji from the City University of New York. And the title of the talk is Non-Hermitian Parity-Hole Symmetry, Flat Band, and Linear Localization. So,
thank you for the introduction. And I would like to thank the organizer for inviting me to this nice place to give this talk. So I changed my title a little bit, as you probably have noticed. So let me start by saying a few words about where I come from. So I come from City University of New York, and or CUNY for short, in a very American way. So CUNY claims itself to be the greatest urban university in the world. So we have the advantage of being very close to the central part of Manhattan. So this is an aerial view of Midtown Manhattan. You realize this building is the Empire State Building, and our graduate center is actually just across the street from the Empire State Building. So upper north, we also have a very advanced research science center, which we share with University of Columbia. So CUNY actually has many campuses. So my main campus is actually down Staten Island. So it's very close to the Newark Airport. So very likely, for example, when you take a flight, landing or taking off from Newark, you'll see an aerial view of Staten Island. And arguably speaking, say that the most noticeable object in the middle of the picture is actually our campus. It's relatively new, so it was founded just a little bit over 6 years ago. But we are booming, and if you have students you want to recommend to our program, please contact me. I'm going to talk about some non-Hermitian symmetries in my talk, and as we know, in the optical regime or photonics platforms, so optical cavities is actually a dominant play force in this field. So if you want to have a feeling of the most recent advances in this field, I recommend this special issue on optical microcavities published by Photonics Research last year. So I was one of the guest editors. Just coincidentally, so this journal also have a special issue on non-Hermitian photonics based on PD symmetry and beyond, published, I think, last month. So one of the guest editors is Gostan Marquez, who unfortunately couldn't make it to this conference. If you also want to have a pedagogical review of the photonics regarding PD symmetry, so I recommend that you read the focus issue on Nature Photonics published last December. So we actually also contributed a piece with collaborators from Feng Liang from University of Pennsylvania and Rami Al-Ghanini from the Michigan Institute of Technology. Yeah. So actually, at the beginning of this, writing this review piece, we actually want to add the beyond part, but because of the length limitation, we couldn't do that. So today, actually, I'm going to focus on this beyond part, not so much on the particle time symmetry, parity time symmetry part. Yeah. So let me start by showing the outline of my talk. So the first part, I will talk about briefly the non-Hermitian parity-hole symmetry and anti-PD symmetry. So I talked about anti-PD symmetry in last year's conference in Bad Hoffman in Germany. So this time I'm just going to give you a very brief overview. So what is anti-PT symmetry, right? We know what PT symmetry is. In optics, just say that your index refraction is a function, spatial function that satisfies this condition if you're talking about one-dimensional system. So when you do a parity operation, you also take the complex conjugation. So that means the real part of your index is symmetric about the mirror plane. Imaginary part is anti-symmetric about the imaginary, about the plane. Okay. So for anti-PD symmetry, it just means that we now introduce a minus sign in front of the one of the terms in this identity. So what does that mean? That means now if we look at the index refraction, now the real part is anti-symmetric. That means you have some part which is real, some part is negative, right? So that means we need to use negative index materials. Depending on the frequency regime, you can actually have different platforms where you can realize negative index refraction. One additional constraint is that, so since now we're talking about negative index materials, we need to also talk about the permeability. Okay, and here in anti-PD symmetry, I require then the permeability to be anti-symmetric as well. Okay? So I talk about the real part. How about the imaginary part? right? From this relation, it's very easy to see that it requires the imaginary part to be symmetric about the mirror plane. It doesn't matter, for example, whether you have gain or loss or some combination of it. As long as it's symmetric, then it satisfies the anti-PD symmetry. Okay, so so let me put the requirements of anti-PD symmetry in a different way. Okay, so now if I refer my induced refraction to be optical potential, then that means my optical potential actually anti-commutes with the PD operator. Okay, realize this is anti-commutation relation. So instead of have a minus sign that we normally have, for example, in PD symmetry, now we have a plus sign. Okay, and this change of sign is actually very important. Okay, it leads to a lot of different implications. Okay, so the next step, what do we do? Okay, now we can look at what if instead of the optical potential, what if the Hamiltonian itself anti-commutes with the parity time operator? Okay, so this is one realization of non-Hermitian particle symmetry, which I'll talk about later in my talk. But here I just want to mention a very simple system where you can realize such a anti-PT symmetric Hamiltonian. Okay, so if you look at this very simple 2x2 matrix that describes the coupling of two oscillators. So if we look at the diagonal element, that means that we need to have some detuning between them. So that's delta and minus delta of these two states. We require that they have some shared loss, which are identical. Okay. The most challenging part is actually about the coupling. Okay. Now we require the coupling to be something unique, right? It's not real. Okay. In the Hermitian sense, it's not, for example, PT in some model Hamiltonians where we have IG for those couplings. Now it's, for example, G and minus G complex conjugate. So one way to actually realize this very non-trivial coupling is using a code-atom system. Okay. So you have a lambda scheme, okay, and by using time as your tuning parameter, you can actually realize this very exotic coupling scheme. Okay. If you want to know more details, check out this paper. So why anti-PD symmetric systems is interesting because, first of all, it has very different implications from PD symmetry systems, as I mentioned. Okay. The second one is it actually is a realization of non-Hermitian particle symmetry defined this way. Okay. So here X is an arbitrary linear operator, so it can be spatial operators, for example, rotation, translation, inversion. Okay. And because of this relation, actually, we can have what is called a zero mode. Okay, so what is a zero mode? Zero mode is that your system has some eigenstates whose energies have a vanishing real part. So that means real part of the energy is zero. Okay. How do we come to this conclusion? It's actually very easy. So starting from the anti-commutation relation, I can actually derive two consequences from this relation. So one consequence is, if I have an eigenstate of my Hamiltonian, and then I apply this combined operator xt, if I come back to the same state, then you can easily show that my eigenstate satisfies this condition, which is basically saying that the real part of the energy has to be zero. Okay? There is actually another possibility similar to parity time symmetry systems if we're talking about the broken phase. So what is a broken phase? The broken phase is if you start with one eigenstate of the system, you do this operation, you actually be mapped to a different state. Okay? So that means now the indexes in this relation are different across the left-hand side and right-hand side. Okay? And this means actually my spectrum is symmetric, not about the real axis like in PD symmetry, but now it's symmetric about the imaginary part, imaginary axis of the complex energy plane. It is. From a mathematical point of view, it is. But from a physical point of view, think about how do you introduce an I in front of your Hamiltonian. It's very hard. And also it has a different implication, like I mentioned here. Okay? And this relation actually is very important when I talk about, for example, topologically protected zero modes in photonic systems. All right, so now comes to my next topic. So now Hermitian zero modes. Again, zero modes are states. Yes, there was a question. Yeah, we're talking about optical systems. Yeah, classical. Yeah. So before I talk about non-Hermitian zero modes. Let me spend some time explaining about the Hermitian version of zero mode. Okay. So in Hermitian systems, how is a zero mode defined? Okay. Of course, we know that the vacuum is probably the zero energy state, right? So, but how do we realize some non-trivial state that has a zero energy? So here, you have to realize that in quantum mechanics, we do have the freedom of shift where the zero of the energy spectrum is. Okay? In condensed matter system, for example, the most interesting energy scale is probably the Fermi surface, right? So the Fermi level. So in that context, in condensed matter context, the zero energy is actually at the chosen and the Fermi level. Okay? In optical systems, of course, we don't have Fermi levels, but then the most common realization of the non-Hermitian systems are coupled systems. Okay, so here is one example. So now if we have one particular state that we are very interested in, for example, this Weisbrand-Gary mode that can exist on one of those cavities, okay? And we ask, what if all the cavities are basically the same? They have the same state with the same energy. So when we couple them, so can we define a zero energy? Yes, we can. Okay, so that's basically just this frequency of the particular state that you are interested in. Okay. So now, how do we get zero modes in a Hermitian system? Okay. In a Hermitian system, we don't have the luxury of non-Hermitian parity-Hole symmetry, but there are other symmetries we can use. For example, one very typical example we will see here is a chiral symmetry, or sometimes it's known as a sublattice symmetry. Okay. How does this symmetry look like? Okay. It basically means that now your Hamiltonian anti-commutes with a linear operator, okay? And again, the consequence of this relation is, now if you apply this operator on one of the system eigenstate, you get some eigenstate of the system. They may be the same, they may be different, okay? So if you want to get a zero mode, that means the two indexes has to be the same. You are mapping the state back to itself after this operation, okay? So when you say this relation, you simply need to remind yourself that this is true, right? Because if n and m are the same, so you have one energy equal to its opposite. That means the energy, real value energy in a Hermitian system has to be zero. Okay? So how do you realize this? Okay, you can look at some very simple model, which actually has been realized in both condensed matter context and in optic context. Okay, so this is what is called the Schraeffer-Heeger model, or short for SSH model. So you have a very simple one-dimensional lattice, and each lattice side consists of, for example, one optical cavities that I showed you earlier. Okay, they share the same frequencies. And on this lattice, you have alternate couplings or tunnelings. You have T, T prime, TD prime, and so on and so forth. Okay, so if you now look at the Hamiltonian of the system, okay, you can basically separate the Hamiltonian into diagonal, off-diagonal form. So what are psi A and psi B? Psi A and B are the wave functions on two sublattices. What are the two sublattices? So they are lattices labeled by A and green colored, and those with B and red colored. Okay. So you notice that two cavities on the same sublattice, for example, there's two A sublattices, do not couple each other. You only have A to B coupling, you don't have A to A coupling, you don't have B to B coupling. That means when you look at this Hamiltonian, you don't have diagonal entries. Okay, you only have this off-diagonal entries that describe the coupling between neighboring A and B lattices. Okay, it's a very simple model. Okay. And so because this structure can show that if I introduce now a chiral operator, it's basically a name in this form, so it's basically a sigma z with 1 replaced by a identity matrix. Okay, and it can show that indeed your system Hamiltonian anti-commutes with this chiral operator. Okay, as a consequence, then you can have a zero mode. So now let's take a closer look at this SSH model and see what is the property of this zero mode. Okay, so I have two parameters I can tuning in this case, so that's T and T prime. If I first choose a setup where T, basically the coupling that's coupling the boundary size to its neighbors to be stronger, so basically you form molecules in this way. So these two lattices form a molecule, these two lattices form a molecule, and so on and so forth. So in this case, we do not have a zero mode. Okay. Then when can we have zero modes? That's when you change the relative strengths of these two couplings. Now let's say that if T prime is stronger than T, then my dimerize, I form two atom molecules in a different way. So now we have a free lattices on both ends of the system. And they are where the zero modes can exist. Okay? So this in real space, if you look at the spectrum, okay, so it looks like this. When t is greater than t prime, then we don't have a zero mode. You notice here a zero mode will exist on this line. There's no zero mode. And now again, let's change the order of these two couplings. Then we have this structure instead. And in this case, we do have two zero modes, one on each end of this lattice side. So next, we can have actually a Hermitian version of the particle symmetry, which is the original way of defining particle symmetry in a Hermitian system. Okay? So it's defined the same way. Your Hamiltonian, instead in this case, is a Hermitian one, but it still anti-commutes with the combined operator of linear operator C and then a complex conjugation operator. Okay? Again, so if you look at how the eigenstates are mapped to each other using this operator descended by this relation, and the spectrum is exactly the same as that required by chiral symmetry, because again, the energies are real, so there's no difference actually in terms of the spectrum for these two symmetries. Okay. But I have to say that if you want to realize the particle symmetry in a Hermitian system, that's really challenging because you need to have superconductors, for example. So that's why optics people don't like to talk about particle symmetry in the beginning because, well, you don't have particle in holes, you don't have superconducting systems in an optical system. Right. So, well, since I'm going to talk about optical systems and photonic systems, I have to say that actually zero modes have been observed before. You have many platforms you can realize this. For example, you have stringed a honeycomb lattice. You can have something like a leaf lattice with the Poisson condensate. Okay. You can also have, for example, one-dimensional microwave coupled cavities, which realize this SS model. Okay. But I have to say that for all those systems, they rely on the underlying chiral symmetry of the Hermitian system. They are not unique to non-Hermitian systems. So the question I want to ask is, can we find zero modes that are unique to non-Hermitian systems? Okay. So for that purpose, let's revisit what particle symmetry tells us. Okay. So as I mentioned, because in a Hermitian system, your energies are real valued, so that's the manifestation of particle symmetry. But if we now are talking about non-Hermitian systems, our eigenvalues of Hamiltonian can be complex valued. So you have to restore that complex conjugate where you have omitted in Hermitian systems. And that leads to the new definition of zero mode. That means my zero mode is only required to have a vanishing real part. My imaginary part can be anywhere on the imaginary axis. Okay. So here I'm going to give to you a cartoon illustration of how a non-Hermitian zero mode can emerge from a Hermitian system where there is no zero mode. Okay. So this is a Hermitian spectrum, as you can see. So all the eigenvalues are real, and there is no zero mode on the imaginary axis. Right? So that's what we start with. So now let me introduce some laws. Okay, assuming the laws are uniform, and all the spectrum does is shifts down in the complex plane. So now I want to introduce some non-Hermitian perturbation to the system, okay? So my spectrum may look like this, okay? And you see that there are two particular modes that are moving closer to the imaginary axis. And it's very likely if I continue increasing the strength of my non-Hermitian perturbation, these two modes will move on to the imaginary axis and then become two zero modes. If one of them have enough gain to reach the real axis, then this is actually going to be a zero mode laser. Okay. So now let's come to this important part of non-Hermitian particle symmetry. Can we realize this really in a photonic system? Okay. So what do we want? We want to use the existing platforms, so we don't have to invent from out of air. Okay. So we also should be able to implement those non-Hermitian perturbations very easily. Okay. So how can we do this? Okay, so let's look at one example that we found a few years ago. So the idea is you start with a Hermitian lattice. Okay, so for example, again, each side is an identical optical microcavity. They couple to their nearest neighbors. Okay, so what we do now is to say that the system still have two sublattices because you can see that A lattices don't talk to each other, and B lattices don't talk to each other. So okay, only A and B lattices are coupled together. Okay. So now we introduce some loss because we know optical systems are lossy. Okay, assume that the loss is the same for all the cavities here. But now when I introduce gain, I want to introduce a localized gain. Okay, for example, I'm only introducing in some particular site in the system. As a result, now if we look at how the Hamiltonian look like, okay, besides the coupling between the A lattice, sublattice, and B sublattice, which we had before in the Hermitian case, now we introduced two diagonal elements in this Hamiltonian. Okay, so those D and DB themselves are diagonal. Okay, and their diagonal entries are nothing but, for example, the imaginary part of each cavities. Okay, denoting their loss and gain modulations. Okay. So if now we have this symmetry, or rather this Hamiltonian, you can show that if the couplings are real, which is basically the case in most optical systems, then by introducing the same Cairo operator, my non-Hermitian Hamiltonian now anti-commutes with the product of C and K. K is again the complex conjugate. So in this way, indeed, we can realize a non-Hermitian version of the particle symmetry in an optical system. Okay. So as a proof of principle, you can look at what are the implications or application you can use of non-Hermitian particle symmetry. Can you use it for topological quantum computing? Okay. So I have to say that it's too early to answer because we have bosons here and we don't really have the property of, for example, anyons. Okay. But there might be some way, for example, by coupling those non-Hermitian zero modes to, say, excitons to form some kind of Mariana zero modes. But before we do that, there are some easier tasks we can achieve, right? We can use the principle of non-Hermitian zero modes, or what I call the photonic zero modes, to achieve a better design of photonic devices to realize some functionalities that we have not seen before. Okay. So one implication is shown in this paper. So as an illustration, what I have here is a two-dimensional lattice, very similar to the structure I talked about earlier, but now extended to the two-dimension. Okay. So we have couplings between nearest neighbors in the x direction and in the y direction. Okay. So now if I introduce some localized pump to the system, my spectrum will go from a state where there's no zero modes to a state that has zero modes. Okay. So the lasing frequency of my coupled system will be exactly the same as the uncoupled state of one of the cavities. So if we look at the spatial distribution, you look at something like this. So now, if I want to pump a different site, okay, so typically when you change the configuration of your system, your laser frequency will change. Here, because of the protection of the non-Hermitian particle symmetry, you can show that the frequency does not change at all. So there it shows some symmetry protection. Okay, and also the spatial profile changes. So you may use those different spatial profiles as a way of coding some telecommunication information for them. All right, and earlier this year, yes? Sure. This one here.
No, 5.
Oh, yeah, this is just the intensity profile of one state. 5 is just happen to be the order of this mode.
And that is like the 5th eigenvalue or something in that arrow diagram.
So here we have 1, 2.
No, in the right figure. In the right
This
figure.
is just zooming part of this energy diagram. So here we have how many states? We have 4 by 4, so we have 16 in total. So those other 14s I'm not showing here. But they are, in the sense, irrelevant because these two states reach the real axis first. So they are the most to be lasing states.
Okay, but then eventually other things will also start reaching the...
It's possible, yes, it's possible. Right. But because of actually the symmetry protection, you can show that the range in terms of pump power for single mode operation is much wider than what you will normally have without this symmetry protection. Yeah. Sure.
Lifetime of the mode.
Yes.
Is it the same thing here, that the imaginary part is the lifetime, or is it something else?
Let me go back to the schematic to answer that question. So here, for example, this imaginary part, K or kappa, is a lifetime. Okay. So now what I'm doing is I'm trying to change how the modes reacts in terms of time. So now if I'm injecting energy into here, that means I can let it amplify on that specific site. So in a way, I'm changing the lifetime, but in a non-Hermitian way.
Is there no problem with applications? If you have a zero mode, it's all well and good, but you are saying it also has imaginary part, which is
Oh, no. So for example, if coming back to this plot, so you realize that if we're talking about physical state, I require the state to be really on the real axis, right? So that's when the latency oscillating freely as a function of time. So there's no decay, no amplifying. So if you pump harder, the nonlinearity will saturate your gain so that you still have a stable latent mode. All right, so that's what I have to say about this case. Now, if we're talking about a system where you also have topological protection, okay, in addition to the symmetry protection, then you can have really a non-Hermitian version of a topological chiral edge state. Okay, if you look at this paper, actually those authors did not talk about the symmetry protection at all. But I hope that after this talk, the message I can take home is it is the non-Hermitian particle symmetry that protects those zero modes. Well, if we want to have a proof, it's very easy. So if we just look at, for example, one of the figures all those provided, okay, let's look at the white dots first. Okay, so those are the basically eigenstates of Hamiltonian before we add gain. Okay, so there is some non-local laws that the authors have introduced, so it's not a straight line here. Okay, they have some modulations. As soon as the energy is being injected into the system along the edge, you see that all the states start to have a smaller and smaller imaginary part. And eventually one of them reaches the real axis, and that becomes the latent mode. Which one it is? It's exactly the one sitting at the zero energy. Okay? So again, that's just the manifestation of the symmetry protection due to the non-Hermitian particle symmetry. All right, so now I want to slightly switch gear and talk about something else, okay? So that is the non-Hermitian Flam bands and defect state. Okay, so what is a Flam band? It's actually straightforward. So if you look at the frequency as a function of the wave vector in a periodic system, we require that there is no dispersion, basically. So this is a constant function. Okay? So how do you realize this? You can realize you use a frustrated system, for example, a Lieb lattice. So basically it looks like this. It's a decorated one-dimensional lattice. So besides this main lattice site B and C on the one-dimensional chain, we also have some off-site A's that couples to this main lattice site. Okay, so you can have different couplings between the vertical direction and the horizontal direction. Okay? So you can realize this, for example, using the couple micropillars, which are based on the, I think, gallium arsenide platform. Okay. So how does the spectrum of this periodic system look like? Okay, look like this. Okay, we have 3 bands because in each unit cell shown here, we have 3 sites. That's the reason we have 3 bands. And then the middle band exactly flat. It's dispersionless. Okay. So if we want to have a non-Hermitian version of the Flam band, so let's take a look at what typically the band structure respond to a non-Hermitian perturbation. Okay. So one of the earlier work is by Professor Christolidis' group back in 2008. So what they shown was if the system has a periodic potential, both for the real part, which is shown here by the blue, and the imaginary part, which is shown here by the red, then you can actually engineer the spectrum of your periodic system in some way. Okay, so this is how the spectrum look like for their system. Okay, you have 2 bands, and then before we introduce this imaginary part, so the band energy is real. Right? So you have some dispersion, you have some gaps between them. Okay? So now if I start to increase the modulation of the imaginary part of my potential, you'll see that these 2 bands actually are emerging from the edge of the boiling zone, okay? And there is still some curvature, okay? But in some later studies, some people show that after the 2 bands, the real part merge, so this part can be flat. And then there was no explanation of why that should be the behavior, okay? So what I want to point out is, well, this behavior is nothing but the symmetry protection due to the non-Hermitian particle symmetry, okay? So here I'm giving an even simpler example. So I have a one-dimensional system with identical sites with identical couplings. Okay, it's easier than the SSH model. So all I do is I introduce laws to the blue sites. Okay, so before I do that, my spectrum look like this. Okay, So I should have just one band, but because I folded about this axis, it looked like I have two bands. Okay. So now if I start to increase my loss, you see that the band edge start to collide, okay, become a single band for the real part. And then eventually the two bands become the single band with a completely flat dispersion. Okay. So this is for a lattice with a unicell with two sides. You can do this, for example, with a lattice of a unicell with four sides. So before I introduce the loss to the green sides, they look like this. If I now turn on the loss, then eventually, so two of the middle bands will become the same and then dispersionless. Okay. So what I want to show here is, even though I'm only showing you the real part, okay, so there is actually some dispersion for the imaginary part of the spectrum. Okay? But the effect of the imaginary part is actually pretty small. I want to demonstrate this using the idea of defect states. Okay? So what I'm going to show is I'm going to introduce some defect on one side of this one-dimensional lattice. Okay? So what I'm doing is I'm making the, for example, optical cavity slightly larger or smaller so that I can have this detuning. Or even simpler, I can just heat up that cavity so that its refractive index slightly changes, and then that introduces defect. Okay. So for this defect, now let's look at how it emerges from the flat band. Okay, so you see the gray line here. So that's a flat band with many modes of a system. But as I increase my detuning, I see a defect state emerging from this flat band. Okay. So now if you look at its spatial profile, okay, it will look something like this. Okay, this is plotted on the log scale because it's interesting feature. It looks like a steps. Okay, so now so this particular spatial profile is achieved by some parameter of detuning and some strength of my loss. So now if I make my loss slightly weaker, so we see that it actually becomes something like this. Okay. So if you compare these two different spatial profiles, you can imagine it as a chain of two different couplings. One coupling is rigid, so it doesn't change its relative strength along that junction. And then it has also another junction which can be tuned by your loss strength or the non-Hermitian parameter. Okay, so this is true for this case for a particular value of delta. If we change the value of delta, the spatial profile changes a little bit, but then the stretchable and rigid links are still the same. Okay, at the same time, if you look at, for example, this exponential behavior, what is its localization length? We show that the localization length decreases monotonically as a function of the detuning. Okay, but at the same time, if you look at the loss of this defect state, it actually has a non-monotonic behavior. So this is just to show you that this change of localization length is not due to the change of loss in the system. It's more complicated. Okay. Besides this interesting observation, you can also show that you can reduce the system to a pseudo-spin model. Okay, so because after all, a unicell only have two sides. It's just like a two-level system. Okay, so you write down the Hamiltonian inverse system. You can write it down as the some pseudo-magnetic field and interacting with some pseudo-spin. Okay, but different from all the previous efforts. So here, the magnetic field is actually complex valued. Despite this very strange property, which is not physical from some physicists' point of view, it leads to very interesting behaviors. So what I'm showing here is that the function of gamma, which is basically L/2, so if I don't have this loss modulation, then actually my lattice has some rotation of the pseudo-spin along this one-dimensional lattice. But as soon as I turn on my loss and then increase it above some threshold, then actually all the pseudo-spins on my lattice becomes aligned. So in this case, white is -1, black is 0, so it only has a sigma x component. I only have 50 seconds left, so I'm going to skip this one and then slightly talk about the linear localization. Okay? So we know that if you want to go from a periodic function to a disorder system, you can just increase, for example, the disorder in the system. Okay? And then there is an interesting question of what happens exactly at this transition. So earlier this morning, we have a comment telling us, indeed, there will be some interesting state like multifraction, factor, and this position. So what I want to show you is, what if we're looking at different transition instead? I showed you that in this SHS model that I can have localized state on the system. So what if we couple this state to a non-Hermitian reservoir? Something like this. Okay, so that's my system with the localized state here. I couple it to a non-Hermitian reservoir. So what happens? Okay, what happens is, okay, so you can have some delocalized states in the reservoir for some band structure that's not flat. If I now increase my loss and gain modulation in my reservoir, I make my band structure flat. In this case, I can have localized states in my reservoir. Okay, this is a log scale plot of this tail, right? Exactly at the transition point, what happens is you have this behavior, which I have never seen before. If you have seen some references, please let me know, okay? So the spatial profile of the wave function itself becomes a linear function. Okay, so that's very striking because no matter which standard quantum mechanical textbook you look at, you will never see this behavior, okay? And you can actually realize this in a coupled waveguide system, which we show here. Indeed, you see that the profile inside the reservoir is a linear function. I should emphasize that, so this behavior is not due to exception point. So we have some problem with the rephrase, and if the rephrase happen to be in the audience, I would like to discuss that with you later, okay? All right, so with that, I would like to conclude my talk, and thank you very much.
You started talking about Anderson localization, but then you didn't continue. I mean, whatever, because of lack of time. I wanted to ask you the question in that context only, like, what is the effect of disorder going to be perturbation on your non-Hermitian flat band? And like, does it matter whether you consider the imaginary part also flat or not? Because I think, you see, like, we have seen a lot of...
Yes, so for example, if we want to define the group velocity of your periodic system, you can show that it's not just the real part that matters, right? So even though I showed you that the real part can be flat, but the imaginary part still has some effect on the group velocity. But having said that, I should say that the imaginary part modulation in a photonic system is actually very weak because actually those are high quality systems. So the imaginary part actually does not play a role. So as long as the real part is flat, the imaginary part does not really play much of a role.
Yeah, but you, I mean, you know that there is an inverse Anderson transition in flat band, weakly disordered flat bands.
Right. So we haven't looked at it yet, and it will be interesting to see how that acts in the system. Yeah.
Yeah. So my question is about this anti-PT symmetry. You see, there are some earlier works on topological insulator phases using pseudo-Hermitian notation. And there, if a Hamiltonian has chiral symmetry, then one can show that that Hamiltonian is, if that Hamiltonian is pseudo-Hermitian, then this is anti-pseudo-Hermitian also. Okay? Now, I'm wondering whether for this particular case also, when you're talking about chiral Hamiltonian and anti-PT symmetry, whether a different set of PT symmetry will make it PT symmetric also or not.
So can we be a little bit more specific? For example, which model are you talking about?
I'm talking about the first part where you were defining this anti-PT symmetry.
Okay, let me go back there. Let me fast forward here.
Yeah, so here, so these anti-commutation relations, right? So what I'm trying to say that there are similar results in terms of this pseudo-Hermitian description. And again, in the context of topological insulator, that if a Hamiltonian is pseudo-Hermitian, and it has a chiral symmetry, then one can show that the same Hamiltonian is also anti-pseudo-Hermitian.
Oh, yes, of course, yes.
Yeah.
So because, like I mentioned here, so the consequence of anti-PT symmetry, or in this more general context, the non-Hermitian particle symmetry is your spectrum is symmetric about your imaginary axis. If you already have a pseudo-Hermitian system, then of course the spectrum is symmetric about the real axis. So you can have actually both symmetry in your system. In fact, the first optical realization of PT symmetry, if you remember, is just two coupled rings. For that system, you have both PT symmetry and what I call the non-Hermitian particle symmetry.
Okay. Yeah, I know that. I know that. So I wanted to see that whether, since there is also discussion about this topological phases, zero modes and all these things, whether in regard to PT symmetry also, whether there is, when the Hamiltonian has chiral symmetry, say PT symmetry is not unique. So one set of PT symmetry, it commutes, and another set of PT symmetry, it anti-commutes. So that the same result here occurs or not. That's what I'm asking.
Yeah, so that's okay. Yeah. So it's basically your system has more symmetries.
Exactly.
Yeah, you can do that. Yes.
So maybe if there's one more question. Okay, let's thank Lee again.
Thank you.